10 seconds, so...
You
say something wrong, we can switch it off.
Yeah, but it will be taking, but it will be still transmitted, yeah. Yeah. It works, it works. Okay. All right. Thank God for giving me the strength to go through all this, I have to say. And I'm really thankful for all of you coming today. It's really an honor. Also, I would like to thank my wife who went through all crazy stuff with me, because I was most of the time staring in the void whenever I was working on this. So I was like, I listened to the lectures for a while, and then I just started to contemplate about the nature of the universe and everything. And it was actually quite an interesting journey, I have to admit. And every time she was worried because I was like staring in the void, and she said, "Are you okay, honey? Is everything is fine?" Because she was like thinking, "This is it. I lost the man. Puku, this is it. All right. Quantum computing, this is for mere mortals, all right? So you don't have to have the background of quantum mechanics. I mean, I'm going to give you the background really quick. May I remind you that that this is the curve which we are going through. I have to cover a lot of ground, and this is going to be an exponential one. So right now we are right there. In 2 minutes we're going to be here, So 5 minutes later we're going to be like somewhere up the skies. So it's going to be really a very interesting journey. So you might ask actually this very interesting question, touching detale, like why do I need to know about the details of things, right? And then the question comes up, and then you ask. So I can actually ask you this interesting question: why, for example, if you would like to divide a number by 2, you have 2 options, right? You either divide by 2 or you multiply by 0.5, right? Now the question here comes, why would I choose to multiply by 0.5 instead of dividing by 2, right? And the thing comes here that when you realize how the logic circuits are laid out, you realize that actually the division circuit is actually a little bit longer than the multiplication circuit. Like when you put out the AND gates and OR gates, you actually figure out that the multiplication circuit is really, really smaller, so it will take less time to actually do the calculations, right? Now, of course, some of the more experienced people, they will talk about shift registers, where you can actually just simply like shift to the right, and then this is it, you divide it by 2, right? And actually, if you have all the compilers right now, they have actually this built-in optimization. So my point here is, knowing the underlying system, how it works, is important for you as an engineer. So if you understand the technology from ground up, like from the basic electronics to transistors up to the logic gates and the Boolean algebra up to the operating system and everything, if you understand this whole thing from bottom to top, you're going to be actually a way, way better engineer, because you actually can take better decisions when you are actually designing your own programs. So this is a very important thing, that you understand the details of this. All right. So one of the things here is Richard Feynman. He actually mentioned. He said it is safe to understand. It's safe to say that nobody understands quantum mechanics. Let me be clear here. He actually said that, but he actually in another interview he was talking about that everybody knows how it works because the equations are there. We know how it works, right? But we don't understand why. And this is the most boggling things about quantum mechanics, okay? So I would like to ask you, do you know what this picture is? No, we don't know. No. This is actually the beauty of the human brain, right, isn't it? You have so small information, you can actually interpret this. But now, of course, all of you know that this is the Mona Lisa. Now, the interesting part here is I've driven my point of the granularity of this talk, okay? This talk, you're going to come up with that talk when you go out from the lecture hall, hopefully alive. You're going to have a general picture of what it is. However, the beauty of the details has been just extracted, which is the math behind the stuff which I'm going to talk about. And this is because if I actually start to introduce the math and then you start to see the actual beauty of the whole picture, this talk will be 7 hours long. And it's going to be, and I need 2 months at least to prepare for this, not 1 month. But since this is for mere mortals, it's enough for you that you can actually can see the general picture. So we're going to have two types of audience. One type of audience who's going to be actually saying, this is ugly, and I would like actually to know more. So they will actually research more using the keywords which I'm going to give it to you out. So I'm going to actually take that month-long journey off of your shoulders. So if you would like to research, you can actually immediately know the keywords, and then you can start actually researching immediately. Don't waste time to find out what is the naming of other things there, right? And if you are actually satisfied with this picture, this is beautiful, I'm going to make it my own wallpaper, then this is great. Right now you can actually still follow people who are talking in keynotes, like in Microsoft Keynote, so you don't go just like bananas and you explode, right? So you understand what those people are talking about, okay? So that's being said, now this is the ultimate question which people obviously like to ask on the Imager, 9gag, YouTube comments and these things. Can it run Crysis or can it run Witcher 3? And I may say a very big nope, it is not for that, okay? So what a quantum computer is for. So there's a very small story behind this, so, which actually quite interesting. Not for you, probably for me, maybe. You know, you might ask what a game developer / graphics developer is actually doing on this task, because it's actually it's actually almost far away. It's like touching edge with computer science. Like it's actually computer science, but it's really far away from my main expertise. And the thing here is, I was actually researching one day. A couple of years ago, I was actually researching in this massive parallel processing on GPUs, and I thought it would be a nice idea that I could actually simulate a full galaxy using Einstein general theory of relativity. So I actually start to study the equations, so I can actually break them down, and I put this n-body simulation on a GPU, and hopefully I will get up a very interesting simulation of a galaxy. I thought it would be a nice exercise for, you know, GPU computing, blah, 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 and all these things. It has been done. It's not something new. But I thought it would be cool to do it, right? And then, of course, like anything on the internet, you research, right? And one thing leads to the other. You know, like how you research on the internet. You research something about the physics, and then you end up talking, you know, reading a Wikipedia page about the history of Sphinx cat and its effect in I don't know, in the ancient Egyptian civilization. This is how internet works, I guess. So I actually found a video, an interesting video, about a year ago, actually November 2016. It was talking about the quantum computing. I didn't understand anything. And I thought that the guy was talking, it was actually talking about this quantum parallelism. You see, it's actually tangible right there, you know, talking about this parallelism nature of the quantum computing, which we're going to come actually to it very soon. And I actually didn't understand the guy, but I thought it was actually quite theoretical and everything. And then a month, like almost a year later, in December 2017, which is like almost a month ago, or 2 months ago, I found the video. Microsoft released a quantum simulator, and my jaw was just on the floor, right? I was like, what the hell? You know, it's 1 year. How, right? And then I said, okay, let me look at this. And then when I looked at this, I was actually stunned because I didn't understand anything again. Because people in Microsoft Keynote, they were talking about things that are a little bit yeah, like weird, right? And it turns out, when I was watching the keynote, the guy was talking about simulating molecules, right? The interesting part here is I had, in 2012, I was mentoring a team doing this Chemicalium project. You can find their stuff in the library. We were actually trying to make molecules all the time, right? With phones, with cell phones and everything. If you actually quite interested, you can find it on YouTube, I think, some of the demos of that project. Now, the interesting part here, when we were actually preparing for this, we actually like took the Mendeleev table, this chemical table, and we took the last two columns on the edges because we could actually combine them with a computer. So you can actually like, based on the valence of the atoms, you can actually start combining things. You can actually start combining, making molecules based on some easy combinatorial kind of equations, like, or kind of algorithms, right? And I was talking to the guy, to the professor of chemistry, and I was asking him, why can't I just take from the middle, and I can actually form my own molecule? I could just simply run an algorithm that just simply start taking these elements and start mixing them up, and then hopefully we'll come up with the answer. And the idea here is, he told me it's impossible. And I didn't understand why, but then he told me there are so many factors. So for example, if you would like to come up with some molecule, you can have, for example, like you have to have a specific pressure, you have to have specific parameters, heat, I don't know. There are many, many other parameters that you have to set up in order for the molecule to start forming, so you can actually make something that's usable, okay? And this was the end of the discussion. Forward, I don't know how many, like 4 or 5 years later, so 2017, I'm watching this keynote, and the supercomputer, which is right now in China, which was mentioned by the professor, I forgot his name, we're going to see him in the slide, couple slides later. He was talking about simulating caffeine on a supercomputer, and the caffeine molecule, this is the maximum which we can simulate with our classical machines right now, okay? So this is just a simple caffeine molecule. You cannot if you add one more thing, if you add, for example, iron to that molecule, right now the computer just cannot handle it. Right now you need a different kind of machine that can crunch this problem, like crunch these numbers, figure out the states, the quantum states of the atoms, how it will actually work out that simulation. So this is one of the uses that you can use quantum computer for, is simulating molecules, making up new materials, okay? So this is one of the uses which you can have. There are many other uses, of course, you can find on the internet, but this is one of the things which actually has been resonating with me because I was actually like somewhat tangible to this. This is what brought me to this talk, right? So for me, this was another giant leap. When I saw the professor actually was holding this chip, I actually paused the video, I maximized the screen, and I paused the video and I was looking at it carefully, because for me, this was the equivalent of this, okay? This is exactly this, for me, right? Because right now, as of this talk, of this year, as of our technology, these computers are actually being saved under very, very cold fridges, okay? And they are in these gigantic kind of sizes. This is exactly the same old computers we had, like the Colossus and the ENIACs and electromechanical computers, when they were actually extremely large. So for me, this was like the same discovery as this, even though it's could be a relatively how can I say, old maybe, the ideas of it, right? And we're going to see how old later on. But this is actually, by the way, this presentation is giving you the edge right now where we are in terms of technology, right? I'm going to talk, just going to bring out something from the history from the back just to map out what I'm talking about in this new, technology here. Okay, so this was the keynote meeting that when they were actually talking about the details of it. Now, of course, for me, it was like all hieroglyphics. Even I'm Egyptian, I didn't understand hieroglyphics, so yeah, it's like it's pretty much the same. So I was like, for me it was like this. So I was like, what the hell, So what this talk is really about is digesting what those people were talking about, right? So yeah, Leo Kouwenhoven, I think this is how his name is pronounced. He is actually the physicist on the team. Krista Svor, she is the computer scientist on the team in Microsoft. And she actually is the first one I saw when she was presenting the video about the quantum teleportation demo, which we're going to see together. And believe me, I mean, when I saw it 1 month ago, I didn't understand it at all. Forwards, you know, like fast forward 1 month later, right now I fully understand what it is. And we together, we're going to fully understand what it is all about, okay? And later as well, we're going to understand what he was talking about, because both of them, they were talking about something like braids and things that are like, and I hate people talking in analogies, because when you talk about analogies, you start taking out the beauty of the matter from what it is actually, okay? So, couple of prerequisites. We have to just, right now, this is the part where we're going to actually go up on the scale. So, a primer on subatomic particles. So what we have here is, when we learned in school, or we as well, I learned in school, that the atom is one of our building blocks of the universe. So we think about it as Lego bricks, right? And we discovered something smaller, which was the electron, which happened to be orbiting around the nucleus. And then later on, we discovered the nucleus, and then we discovered what is under the nucleus, right? So we discovered that we have quarks, and you have two types of quarks. So you have, I mean, you have protons and neutrons, and then you have quarks inside them. So we get smaller and smaller and smaller, right? And the quarks, you have like two of them, as far as I remember. So you have the up quark and the down quark. Okay, this is how they are called. I mean, I pointed out, but they are not like this anyway. So just to be clear here, they're just names that has been named like this. There is no absolutely reason why they are named an up quark and a down quark, other than just using it that way, right? And this is it. You cannot divide them. Okay, and this is what the interesting part, when we come later on, people were thinking all the time that you cannot subdivide an electron. So an electron, no matter what you do to it, you cannot break it into half, theoretically. Later on in the presentation, we will see how this is actually happening, which is kind of mind-boggling, I have to admit. So people were thinking back in the day that this is actually the building blocks of the universe. So you can actually have this Lego brick mind of how we are being built. However, honestly, I have been exposed to so many fields in these things. I've listened to a guy who was talking about the quantum field theory. And this is, in fact, what we are made of. We are made of quantum fields. So we are made of, we are like have some sort of a frequency that surrounds us, and we are interacting with it. So we are like having multiple fields that are layered above each other, and then the reactions which we see is just how these fields are interacting with each other. This is what this quantum field is all about in exactly 2 sentences, which doesn't do it justice, but you get the picture, okay? But feel free to search on the internet. There's a nice lecture from the Royal International Academy. There is an English guy who was talking about the introduction to quantum field theory. It's really beautiful. And this for me was a mind, just my mind blown, honestly, when I knew about this, because right now a lot of things made sense, what you have read before, and the sci-fi movies and all these things. So, so we are made of actually quantum fields, and this is actually a very important thing to keep in mind, because I'm going to rely on that to describe what's coming up next. Okay. Another primer on the subatomic particles. When you actually look at the particles which we have, we actually divide them into 2 major categories. So we have fermions, and then we have bosons. Okay, I think you heard about the Higgs boson, most probably, from the news when we discovered it and everything. So, by the way, before I just forget, because these guys do have a spin. They spin. Like Earth on an axis, okay? And if you actually expose them to a magnetic field, they start actually to wobble, like a what was the kids? There was a kids, like a children game that I forgot how it's called. Like, it's just in English. It's just like it starts to you know, like throughout wobble in an interesting frequency. And physicists actually could figure out exactly what was that number of that frequency of that's wobbling. So, so technically speaking, bosons, they have discovered that they have a 0 or 1. Most probably they can have a 2 or 3, but I don't know if we have discovered them yet. But we know that they have a 0 or 1 spin, and bosons have these couple of primary particles we have. So they have the gluon, which describes the strong force, Z and W bosons, which carry the weak force. Right now I'm just giving keywords. You guys actually have to research about what does it mean, the strong force and the weak forces and everything. Photon, which is the electromagnetic force, and these are actually the ones which we have in the bosons category. However, fermions right now, because by the way, I'm going to mention fermions later, okay? Be ready for the quiz, which is going to come after this. I'm just kidding. So, fermions, which are actually split into 2 categories, quarks and leptons, okay? They have a half spin. Actually, when I tried to search for the visualization of this, I just couldn't understand it, and I just said like, okay, just, yeah, I'm fine with the word half spin. And the fermions are the up and down, charm, strange, top and bottom. This is how they are called, actually. Again, people run out of English words, so just like, you know, okay, this is strange, and this is charm, and that's it, you know. So basically speaking, from these fermions, if you actually take 2 ups and 1 down, you create actually a proton. And if you grab a 2 downs and 1 up, you give a neutrons. Okay. So this is basically how things are actually constituted or made. These category of people, okay, I'll call them people. They are called baryons, okay, and they are actually interacting with those fields. So, for example, when you have a particle that interacts with a photon, electromagnetic force, you actually can start seeing it, okay. So this is basically the rough picture of what we are talking about, okay? Now, in order to understand the concept of what I'm going to describe in terms of the programs, I have to go back. Honestly, when I don't understand anything personally, I just start to go back as far as I can so I can understand what the heck was told, what these people are talking about, right? So I'm actually going to grab the double slit experiment, and I'm not going to use analogies. I'm not going to use Schrodinger's cat or anything because I hate it. It's for me is more confusing than anything else. And I'm going to describe this double slit experiment exactly like Richard Feynman described it. He described it as it is, as it happened, rather than just give you some stupid analogies. So, actually, even Schrodinger apologized about giving the analogy of the cat, honestly. I mean, I was researching, trying to understand if he's actually was following it up, like he's pushing this idea, but he apologized later. Now, so you have this problem of particle duality, this particle wave duality, and everybody was probably they understood or they heard about it. So the first thing is you would actually, for example, grab a machine gun, okay? And then you actually start shooting bullets. Now here's the important part. There was this discussion a long time ago from Newton and Maxwell and the years come after. So like for 200 years, people were discussing if the particle is in fact a wave or a particle, right? Like, so they come in lumps, like they come in as a whole piece, right? So what they said is we're going to actually use a gun, right? Let's simulate it. So imagine you have a gun and then you have some sort of a wall with 2 holes in it. And that gun is actually like vibrating, right? So it's not shooting in one direction, but just simply like up and down, right? So the gun will actually start ricocheting from the hole somewhere, and at the end it will end up on a detector, right? So you will actually like have the detector sitting right there. So when a bullet comes, and it has to be an indestructible bullet. So when the bullet arrives as it is, hits the wall, it hits the detector, we take it, right, in our hands, okay? And what happens here is when you keep both of the holes open, you end up with such a graph, right? So when you sum up the number of the bullets which you grabbed off of the wall, okay, with that detector, you will end up with something like this. If you close one hole, you will get this. If you close the other hole, you will get that. But if you open both of them, you will get this, okay? So we are actually quite fine with it. This is like the summation of both of the graphs, right? Now, this is actually quite plausible. This is just fine, and we are actually okay with this. Now, let's go to the waves. So you actually grab a wave source, which is, for example, something that is actually extremely precise, that's actually going up and down in the water, causing waves to, causing these ripples of waves. And then you have another wall with two slits, like with two opening. And then you have some sort of an absorber, and then you're going to have a cork. And a cork in English is the thing which closes the bottle of wine. So like, boom, yeah? Chip, yeah, exactly. So that's the thing. So you put it there, and then you start actually detecting things, right? And then you measure how this thing is just jumping up and down. And at the end, when you close one hole, you get this. When you close the other hole, you get that. But when you open both of the holes, you get this, okay? Which is this wave part. So here is, I think it's called the destructive, oh, I forgot what it was called. Like when you combine two things and then they destruct, so you get actually, I just forgot the terminology right now, it was on the tip of my tongue. And then when you have this constructive part where two waves are meeting and then they actually form a higher wave, okay? So you have that. This is why you actually get this interesting wave with that kind of look, isn't it? So at the end, what happened here is when people said, okay, we're gonna actually start simulating this. And we're going to actually grab an electron gun. So we know how the wave behave. We know how the bullets behave. Let's talk about how electrons behave. So they said, okay, I'm going to actually push in, I'm going to put an electron gun because we think that electrons comes in lumps or like bullets. Okay? And of course, you actually open these two slits, and then you actually put in a detector, and then the interesting part here is, which I actually jumped off of my chair. So the interesting part, I was listening to that lecture. This lecture was held in 1964. I remember clearly, I watched it actually twice because I was enjoying that lecture, I have to say, called me sick. The guy, during the lecture hall was so quiet when he announced that after actually shooting that electron thing, they were getting this, right? And I actually almost jumped off my chair because I know that there is this particle wave, duality. So maybe we could have something a little bit different than this. This actually, this clearly came out like this. This is the surprising part. Okay, so for me, this was like I paused the video and I was staring at the void again, right? Where my wife is asking, okay, are you okay, you know? So the interesting part here is this, okay, I'm gonna hide one. Okay, I'm gonna hide one hole. They are getting this. I'm gonna hide another hole. I'm getting this. I open two holes, I get this. So you say you're actually getting a little bit smarter. And you say, okay, fine, this is good. I'm going to actually put a source of light right there, okay? And I will start counting who actually comes through these holes, right? If I see somebody flashes through hole 1, by the way, just to let you know, before I actually carry on with the experiment, with that observation experiment, when people saw the waves, that means actually that the electron have passed through the two holes at the same time. This is where the troubling part. This is what scared people off. If I was a physicist, I would be scared. Honestly, I would, shit my pants right there, because I would like, this is not normal, isn't it? Now, you start questioning the reality. That's the problem, right? And so you actually put this light detector right there. You actually just put the detector right there, and then you start waiting for the electrons to pass through. And if it flashes at hole 1, then you just simply have a table and you just write out, it flashed at hole 1. If it flashes at hole 2, you say, okay, this is flashed at hole 2. right? And then you start actually doing the counts. And the interesting part here is what people getting was this. Interesting, isn't it? So people, they say, sorry, let me just move on here. So people were thinking, if I actually put a light source and I'm waiting for things to flash, I know exactly where this electron have passed. That means that most probably this light source was in fact quite strong. So maybe the photon had some sort of an interaction with the electron, so it actually knocked it out, blah, blah, blah. So most probably it just affected the result, right? So they said, okay, fine. How about this? We turn this off. We make this running slowly, like it just clicks, then clicks, then clicks. So it's really slowly. Let's see how things are building up. And the interesting part here is, while this is turned off, it builds up to this. So, you know, 1 point arrives here, 1 point arrives here, 1 point arrives here, arrives here. And after some time, you build up that wave. So I said, okay, fine. Let's turn on that light back again. And then they get, again, what they are getting with a bullet. And then they say, okay, okay, fine. I will take this, and I'll make this dimmer. And so dim that it actually, I cannot, you know, it just doesn't, it's trying not to affect whatever is passing through, okay? So this is another smart idea. So the people will do is, you have actually you're going to have a table of 3 columns. One column is pass through hole 1. The second column is pass through hole 2. The third column is I didn't see, because the light is so dim, the things start to pass and you didn't see them. The funny thing here is, the less and less dim, so we actually miss the dimmer this part of the light sources for the detecting, the column of I saw actually start to map out like the gun, and the part which I didn't see start to map out like this. You know, nature is playing with you games, isn't it? It's kind of actually intriguing, you know, and funny at the same time. So, and scary also at the same time. So at the end, people believed, so I will actually say I will be smart and I will turn this off completely. Again, I get this, right? So as long as you are not consciously measuring, this is the part where it comes into quantum computing later. If you are not consciously measuring the electrons which are coming through, then you will actually have this interesting superposition of having electrons probably passing through 2 holes at the same time. From this just experiment, people start to question reality, because right now you have this multiverse idea. And Heisenberg uncertainty principle was actually describing this. Schrödinger, he made his Schrödinger equation, which actually describing the particle duality nature, right? The wave particle duality nature. This equation is actually describing just this. Okay, what this is happening, which actually for me makes the physicists are the best reverse engineers in the world, right? At least I look at them that way. I mean, it's kind of sound diminishing to say the physicist is an engineer, but for me it's like they're observing the nature and then they figure out the equation for it, right? It is the same thing like when I give you a piece of electronic and I tell you reverse engineer that and give me the code which actually made that, right? So they actually figure out this, you know, how they observe the nature, they guess it out, and if the experiment worked, then this is great. This is the code, this is the program which describes how nature actually functions. So that's why quantum mechanics without math is just like, it's a tasteless thing, I have to say. And it's not that difficult, I think, when you think about it. All right, so being me, not convinced, because I was asking myself the question, this is the problem where I actually stare in the void again, why I'm not like this? Why am I not able to pass through 2 holes at the same? Why cannot just, you know, go in these parallel? Why not that parallel like the particles? And it turns out that according to the Heisenberg uncertainty principle, and I implore you that you actually research about it because it's actually quite interesting, and please listen to that lecture from Walter Lewin. It's lecture 34, Classical Mechanics, 8.1, I think. I remember still the lecture number, okay? He was talking like this. First, just to give you a really quick primer here, whenever in physics you are starting to describe positions, you have some sort of uncertainty, okay? So if you position something, you have, or you actually, if you measure something, there is some sort of uncertainty. So if you measure your height, you say, this my height is 1.8 plus minus 2 or 3 centimeters, right? When you lay down, you actually start measuring with a certain uncertainty, okay? So there's also uncertainty if you take an object, and this is the interesting part. If you take an object, like a billiard ball, I actually quoted him right there from his lecture. If you take a billiard ball, okay, and you calculate the Heisenberg uncertainty principle on it, and you push it with that speed of that number which came out from that formula, you actually will move. You'll move that after 100 billion years, it will move 100th of a diameter of an electron. So there is as well uncertainty in the position, but however the uncertainty is so small that it's absurd that you say that this object is still at time 0, right? So what is Heisenberg uncertainty principle saying? So just to be clear here, once your mass starts to increase, the observation, the act of observation doesn't affect you anymore, doesn't disrupt your wave part, okay? What other thing that Heisenberg uncertainty principle is saying is that you can calculate only one of two. You choose one of two. If you would like to calculate the position of an electron, you will know immediately where it is, however, you don't know its momentum. If you measure the momentum, you cannot measure its position, okay? Which actually going to bring us to another paradox later on in this lecture, because people are just simply destroying what other people are saying before. This what actually killed me while I was researching this. Because they're like, okay, I understand this is impossible, then it became possible, you know. Which is kind of crazy, I have to say. So after this, I was exactly like this cat. So, yeah, but yeah, because I understand right now, hey, I'm still the same, I'm like this as well, but I'm on a very, very tiny scale. I have some sort of uncertainty still, right? Now, of course, I'm not like a billiard ball, I'm much larger, so most probably my uncertainty is like, hey, tiny. Now, try to describe that to your mom, and you tell her, okay, mom, the cup which you are putting in the cupboard and you close it, most probably it's there and it's not there at the same time. Now, that will be a very interesting discussion. Hopefully you're going to get a slap and she tells you, you know, like, what the heck are you talking about, right? So let's get back to a very interesting concept which we need in quantum computing, which is this idea of quantum entanglement, okay? So the idea here is when you actually, I mean, you can find it even more in quantum biology. It exists. I learned about it. It's fun that you look at biology, how it works like that. When you apply energy to an electron, if you knock it off, okay, it can actually happen to form two electrons, which is going to be the one which is, let's say, an electron and a positron, let's say, okay? Because of an energy, you can actually form an entanglement based on an energy, by the way. So you can actually apply a force that actually creates an electron and a positron. And by the way, the positron is the antimatter of an electron, okay? So this is the opposite. And they happen to be, some people, Einstein like to call it correlate. Some other people call it, some other scientists call it linked. I'm mentioning the two because I'm not having this enough knowledge to say I'm biased towards one or another, okay? Because in science you can only be biased, you cannot be prejudiced, by the way. So you have those two interlinked. I will call them interlinked for now, just for the sake of the argument or pedagogical kind of reason. And what happens here is they are always the opposite. They happen to be the opposite. all the time. Because, I mean, when you think about it, an electron is negative and the positron is positive, and they have to be the opposite. One is spinning up, one is spinning down, it doesn't matter. However, here's the interesting part. When this energy happens, when you get this entanglement going, they actually come out with a shared wave function. And this is very, very, very important. Okay? So if you remember from the double slit experiment, an electron was passing through and it had its own wave function. So it actually came out in form of a wave. But if you have two entangled particles, they share a single wave function. So once you measure one, the other one is immediately determined. Okay? And you break the wave function. This is it. And if you try to measure back again what happened before, you can't. You will get something random. So that's why quantum states are extremely fragile. And people are doing interesting tricks in quantum computing just to avoid that. Okay? So how actually quantum how can we force this entanglement? Okay? This I stolen from, by the way, all the nice graphics I stolen from Google and Wikipedia, and all the bad graphics is mine, and you can see it immediately. It's like, yeah, this is him, this is me, done this. So imagine that you grab two qubits, okay? I will describe a qubit what it is later. And then you actually expose them to laser. This is the ion trapping technique, okay? And you put them in the quantum entanglement state. You separate those two, you send up one to some guy, and you set up the other one to another guy. By the way, this can be transferred to an optical wire or whatever. This is how people actually tested the quantum entanglement, by the way. And what happens is, upon measurement, once you measure just only one, immediately the second one is determined. Okay? The trick here is when you measure, you have to measure along the same axes, because electrons have you have this XYZ measurement. So if you measure along the x, so if you expose it to this electromagnetic, because how you will know that the electron is actually spinning up or down is by just simply passing it through an electromagnetic field, and you will know immediately if it is up or down because of if it repels or not. So you will know the direction of the spin. Okay. So yeah, so knowing this will determine that, and we will use this in order to teleport information, which is actually an interesting topic. So how people, so I actually, before I go this, I actually covered the particle wave duality part. I've covered how entanglement works in very rough manner. You should see the math of these things, it's important. And what else? And the Heisenberg uncertainty principle, which is also important for this, for the upcoming next things. So there are many techniques for building a quantum computer. We have this ion trapping. Ion trapping is based off of the 2012 Nobel Prize, by the way. And I think this is what IBM is using, because IBM is building their own quantum computer. Topological quantum computer, this is what Microsoft is working on. This is actually based off a Nobel Prize 2016, which is actually quite close. Linear optical quantum computation, which is based on photons. We have that. I don't know. This was actually suggested, but I forgot who was actually suggesting it, and I don't know if somebody is using that. There is another group in Australia who's actually simulating a quantum computer on a chip. So they are taking a transistor, they're inserting a phosphor atom, and they are making these quantum calculations based on an electron and its nucleus of a phosphor atom. Okay. It's actually quite interesting. I think Professor Morello, I think this was his name. I think he actually describes it very, very beautifully. I think you have to listen to the guy. You see, one of the problems with building up a quantum computer in general is this fragile state, because the moment when you look at things, the moment when you start interacting, just the moment you interact with something, even by just looking, everything just breaks down and goes to this classic mechanics of the nature of things. And people got out with interesting tricks. Okay, so we're going to talk about these tricks later after we pass through the primer. This is the only math which you're going to see in that slide. I condensed it all in one place, so you will not be, like scared. But this is actually quite easy to understand. Don't worry, I will go through it. This is called the kit notation. Okay. By the way, this is just half of it because there is the bra notation. The bra, you get the point, right? The bra. Okay, so you have the bra kit. Actually, it's called a bracket, but it's a bra kit notation. This just only that part is the kit notation, and this is what you actually would like to have. And what the probability actually, if you look at Schrodinger's equation, it's actually written like this. By the way, this is a simple shorthand way of writing a one-column vector. It's like this. Wait, where is it? Where is it? Wait, where is it? I think I had it. Ah, there you go. Here it is. So this is the one. So this is how it's written. So it's actually a fancy way of writing just a vector. It's just another way of writing it, and this is it. If you look at the other side, because the other side of it will be like somewhat like this, so you have another angular bracket closing it. Here actually is your matrix. Usually it's called the Hermitian conjugate matrix. It's actually right there. Go ahead and read it. The Hadamard gate, which you're going to see later, is actually relying on this idea. Okay, so basically speaking, because we have a qubit, it's actually it can inhibit a state of 0 or 1 or both. Okay, and how this is the both part? Do you remember this like this double slit experiment? It could actually be both. It could be one of those two, right? So it's actually being written like this. The alpha and the beta are actually the amplitude of that wave side of the world. And this is actually your probability when you think about it. So alpha squared plus beta squared, they have to equal 1. And this means that when you start measuring the qubit, it has to collapse to one state. Okay? And even if you put a qubit to a 50-50 state, if you actually simulate it, and there's this IBM Q experience where you can actually like push an element, and then you get the you push the qubit through a superposition, you can get, for example, a probability of 0.5 and 0.4 or something like that. The main thing, 0.55 and 0.45, doesn't matter. And then when you actually sum them together, they're going to be equal to 1. Okay. Now, how do you determine alpha and how do you determine beta? And they are actually determined based on this basic theory of or basic rule of Pythagorean rule for calculating a vector on a triangle, right? So the hypotenuse thing. By the way, when you see this is actually written. By the way, the whole quantum mechanic thing is actually being written in the complex vector space. So that's why you have complex number right there. Sometimes people actually going to see them in books, and in some papers they write it in this real number it's like they write it in this real number notation so they don't complicate the calculation. So for people who don't have this background, they can easily follow. Okay, so if you have actually 2 qubits and would like to know how many states they could be, so this is how you actually write it down. So you take the kit notation. So you have either it's going to be 0, 1, 1, 0, or 1, 1, and all of them written in that column vector format. Okay. So instead of people writing like this, they just simply write it like this. So at the end, when you write it down, for example, a superposition of two qubits, then you're going to have 1 over the square of 2, which is actually related to this Pythagorean theorem. 0, 0 plus 1, 1 divided, I think, actually this is this, 0, 0 or 1, 1. And if you actually solve this, if you start multiplying matrices and solve this, you're going to actually get out with, if you can actually grab this 1 over square root of 2 and square it exactly like this alpha and beta, you're going to actually get half. So you're actually going to get 50-50 state. Okay? So this is basically the math of it. I'm just showing you this so you can understand what are the namings of things. You go ahead and research this. It's actually it's interesting and easy. It's not that really difficult. Back to quantum gates. You know this notion that you have, you can simulate all circuits using NAND, I think, NAND gates, as far as I remember. You have, we have like, these are the most famous gates. The X gate, which is actually inverting a qubit. So if it was up, then it will become spinning down, or if it is 1, it becomes 0. Because the problem, I researched this, I just really forgot. There's a reason why when it's actually down, it is 1. Some people actually, they said they don't know. Actually, I just dig deep, there is a reason for it. I just implore you that you guys research why it was like that. But there is actually a mathematical proof why it is actually pointing down, which means 1. The Z, which is actually a phase shift for the, if you actually take a wave and you phase it, so it doesn't do anything other than just simply phasing it. So this is the Pauli Z gate. You have the Hadamard gate, and the Hadamard gate is actually putting the qubit in the superposition. Okay, if you would like to put it in this quantum state where it's actually just, you don't know where is it, in the universe, this is the gate which you use. And everything is simulated by matrices, by the way, and there is a very good reason for it. Okay, it happens to be something regarding the braiding of how, the math behind how actually quantum computer has actually been made physically, and also the math behind the theory behind this stuff. The control NOT gate, okay, the control NOT gate is quite interesting. This is the control bit, this is the controlled, so this is the control and this is the controlled guy, okay? If this becomes 0, if this line is 0, and this is 0, then the outcome is 0. If this guy is still 0, and this one is 1, then the outcome will be 0 and 1, okay? As long as this guy is turned off, nothing is going to happen. Once this guy is turned on, okay, now the interesting stuff is going to happen. It's going to actually exactly act like the XOR version of our normal gates. So if this is 0, if this is 1, sorry, if this is 1, and this is 0, then the outcome will be 1, 1, okay? XOR the other guy. If this is 1 and this is 0, then you're going to have, no, sorry, if this is 1 and this one, sorry, I mentioned that, yeah. So this is 1 and this one, then you have 1, 0, okay? So this is this part of the inversion, okay? And actually you can, the interesting part about this quantum computer is exactly the same like in nature. The information can never be lost, and you can trace them back. If you think that the information is being destroyed, you are wrong. So if you burn up a paper, the paper hasn't gone, it just has transformed into something else. So the information, if you look at the world, the universe as an information, doesn't get lost. And this is the interesting part. All these unitary matrices, they can be traced back, including the C0 gate. You can trace it back. Hadamard gate, for example, if you apply it twice directly, like so, if you take a qubit, you put it in a superposition, you apply the Hadamard gate again, you will end up with the same qubit again. Okay, so this is an important part. And one of the other part is this Hermitian conjugate, because if you look at the matrix of the Hermitian conjugate, it is the same thing. If you multiply the same thing, if you multiply a qubit by that, if you multiply a number by that Hermitian conjugate, twice, you will get the same number back again, okay? Now, let me take an example. I will take the famous 2 victims in cryptography, which is Alice and Bob, right? They're always the most famous victims in there. And they are talking about, they would like to communicate a 2-bit of an information using a single qubit. So what they do, they say, okay, I'm going to actually take, I'm going to actually make a quantum entanglement. How do I do that? I push 1 qubit through a Hadamard gate, and then follow it up by a C0. Now, if you look at C0 carefully, it's actually an entangler and unentangler. Why? Because if you actually put this to 1, and this passes through, and this passes through, if this is 1, so 1, 1, this is going to be 0. And if this is 1, 1, this is going to be, sorry, so 1, 1 is going to be 0, and this is 1, 0 is going to be 1. So this guy is always the opposite of the above. So it behaves like quantum entanglement when you think about it. They're always the opposite. So if you would like to do the quantum entanglement part as it should be, you push a Hadamard gate through a C0 gate. Okay? And then you send to Bob his stuff. You give it to him. This is it. So you actually, until here, we are done. Okay? Now, what Alice should do, she will apply whatever operation on the qubit she has. She doesn't observe it. She just simply passes it through another gate, which is for us is going to be like passing it through another, I don't know, magnetic field. I'm just saying, you know, like just out of, I'm just pulling that out of my ass, so just for you to know. So for example, right now, right here, I've used the X, so I flipped the bit, and I used the Z in order to phase shift it, okay? If you look at the math behind those two, this is actually sending 1, 1. Later on, you pass this to another C0 gate with a Hadamard gate, and then you measure the two. Okay? And then when you measure the two qubits, so actually what happens here is Alice will actually do the modification on one qubit. Bob will just simply have his qubit waiting for Alice to send her qubit. Right? And then when Bob receives the qubit, he starts to do the measurement, and then he will get actually 1, 1 in that specific case. Okay? Now, do you remember the pixelated Mona Lisa part? The beauty is not there, right? Because you don't understand what the heck is this. You have to see the math of it. Okay? If I actually start mentioning the math, there's going to be a really long lecture. So I really omitted that part. Okay? So, okay, this is a little bit... Yeah, I mean, you can actually start arguing. This is actually not that very clear. So I have another example, which is the hello world, which Krista was talking about in her video, okay? Quantum teleportation. So how quantum teleportation works? Now, first of all, there's this idea of teleportation like Star Trek is actually quite similar, you know? And in fact, you don't teleport a matter. The matter doesn't teleport. You actually just simply sending the information. Now, what Einstein didn't like about the teleportation or the quantum entanglement in general is because this instantaneous interaction, quote unquote interaction, is happening faster than the speed of light, and it violates the general rule of the general theory of relativity. So, in fact, quantum teleportation doesn't violate it. If you look at the quantum teleportation, this is why people start to have ideas. What if I had this idea? Can I actually just use, if I'd like to communicate something, I could use this as Morse code, 1001, you know, just use it as a Morse code like that. And it turns out, the moment you start measuring this, you break that connection, and then you cannot actually do anything anymore. And it is actually more of a probability, a statistic probability. You measure this, it has a spin up. This immediately knows that it's a spin down. You don't know beforehand that this was a spin up or a spin down. So it cannot be used for communication. So what you do is Alice is having her entangled particle or qubit, right? And Bob has the other half. And what Alice will do is having her information, and she will actually push that qubit into one of those gates. So for example, if this was a 0, I will not touch it. If it was a 1, I will just pass it through an X gate to flip it. So it becomes 1, if I would like to. Okay? And what she will do, she will entangle both of those two. Okay? Now here's the interesting part. This is really difficult, by the way, to pull out, because everything is so fragile. When you start doing this, you introduce something which is called this quantum decoherence, where things just immediately reset back to the classical state, which I'm going to show you later on in the next 3 or 4 slides how the computer works, and then I will release you from your agony. So what Alice will do, she will actually put a quantum entanglement she will use another qubit, and she will actually put them all together in an entangled state, and then she will measure. Okay? So if imagining that I know that this is up, okay? Now, when I measure this, if I look at those two, and I know that they are different, and the outcome is different, okay? That means that this was down. That means that this was up, right? When you think about it, okay? And what Alice will do, she will actually communicate through phone line. She will call the guy over the classical methods of this speed of light methods, and she will say, hey Bob, they are different. This is why quantum teleportation is actually secured for communications, because people, whoever is hearing over the line, they will hear just different, similar, different, similar, and they don't understand, because this information just doesn't make any sense, right? Because it all depends on the quantum states, and nobody has the quantum states. Now the interesting part here is, if you eavesdrop in the middle, you'll break the whole thing. You immediately decohere the whole thing, so the whole thing's collapse. So this is actually quite ultra-secure channel. Chinese, quite lately, I cannot remember which year, they have managed to quantumly teleport information along a 3 meter by 3 meter tank, water tank, sea salt, okay, sea water tank, okay? Now this is a very important thing, because what it means for us is that a submarine could be submerged and can be communicated with while it is being submerged. Because radio waves cannot pass through the water, through the sea salty water, okay? So you can actually keep this secure downstairs. Actually, even right now, the submarines can communicate while they are under the surface, because they just simply like start putting some antennas right, you know, close to the surface, trying to be not detected, you know? But at the end, people could use this idea that you can actually submerge a submarine, and then you can communicate with it using quantum entanglement, okay? And it will be completely secure, nobody will know about it, okay? So now you know how this thing works. This is the code which Krista shown. Now the code, honestly the syntax, it doesn't matter, because if you are a developer, the syntax for you is just a language. You speak the language like the same, like you're learning English or Bosnian or Arabic or whatever, right? So what she does here, she assigns two registers, two qubits. One is the message, one is there. There is Bob, the destination, okay? Now she will actually take the message. If the message was true, by the way, originally, when you're preparing the qubits, all of them, they are in this ground zero state. Okay, sorry, in the zero state, ground state, it will be quite dangerous thing to say. So if the message was 1, then I will just simply flip it with an X gate, because we know that the X gate is the NOT gate. It will just simply start flipping qubits, okay? And then she starts teleporting it. Teleport that message there. Now, here's the Alice side of the world. Alice actually will be here. She will pass her quantum gate through, so she will pass her qubit through a Hadamard gate, then a C0. So right now they are entangled, okay? Sorry, the information, hang on a sec, message, not yet. So here is the, here's the register. So she will actually push that here, that Alice, she will put herself into a quantum entanglement with Bob, so establish that initial connection. And then she will take the message and put herself in a quantum entanglement with that message. And then she will start measuring it. Now, if they are actually, if the message is 1, she will measure around the z-axis. If she will pass it through z. If the measurement was, if the measurement of here, so if they are different, so this is actually, like, how can I put it? This is actually telling exactly the same word which I said about if they are the same or different. So if they are the same, then it will actually measure it on one gate. If it is different, it will measure it on another gate, okay? Just to make the long story short. And yeah, so, and here right after this is execution, she will just simply start to ask if this measurement, if I've received successfully the actual qubit, right? If they have received if I've actually could reconstruct the information. By the way, the moment you do this, this whole thing breaks down. So you have to construct a new qubit. right? So if you look at the code, I actually forgot to put a screenshot of the code. The C# code, you see it is just simply keeping constructing a new qubit, because they were doing this demo for 8 times in a loop. And every time they're constructing new 3 qubits for every time they send the information, because once you measure, everything collapses. Okay? So this is how the circuit looks like. It's musical, isn't it? It looks like a piece of sheet of music. This is the, you know, I always say that the best solutions are always the most elegant and the sexiest, I would say. So you have a sexy code, that means it's an elegant solution, right? So there's the final part of our talk. Anybody still alive? No? Okay, okay, good. How Microsoft is actually building their quantum computers. And when I was actually researching this was based on the quantum topology and the quantum fractional statistics and a lot of braiding. When I just read this, and I was like this. So this is me. So what the heck is this talking about? So yeah, that's, you know this month was a hell of a ride, I have to admit. So Peter Tate in the, I think it's in the 1600s or something like that, he and his colleague Kelvin, the guy who made the Kelvin scale, I forgot the first name of the Kelvin guy. So it sounds ignorant, but believe me, just all of this is just bungled my mind. The guy was talking about this topology, the idea of topology. They know quantum mechanics yet, okay? So he was actually interested in the knots. And I'm not talking about the knots as the knot as in OT, I'm talking about knots, right? So this is the father of the knot theory, okay? Now this is actually easy to understand even for a 3D modeler. So if you actually look at and this is, by the way, this what I'm going to talk to you about is based on the Nobel Prize of Physics 2016. Okay, and the guy, the interesting thing here, the guy actually came in, the professor, he came in and he just simply put out a bagel and he put out a donut, right? So he just was describing these stuff and how they are equivalent to each other, okay? So what happens here is if you look at a donut and if you look at a mug, mathematically both of them they are the same. Why? Because both of them they have one hole and that's it. If you are a 3D modeler, you can actually push your luck so much that you can actually take a donut and you make a mug out of it. Because you are morphing it. All the thing is, what you do is just simply morphing the actual thing to take the shape of a mug, right? But still the hole is there. If you start deconstructing this, if you suddenly have a bagel which has 3 holes, this is not the same equivalent of a mug with one hole, right? You cannot look at it the same. And this guy, Peter Tate, he was actually interested in this idea of knot theory. He was like thinking, if this knot is equivalent to this one, okay, is this the same? And he was actually solving it mathematically. And he spent all his life, I guess, just solving just this idea, which, like, I don't know, what, 200 years, 300 years later, people actually found it quite useful to solve the problems of quantum computing, surprisingly enough, okay? They're actually being solved using something which is called Kaufman invariance. I think it's called Kaufman invariance. I will mention that in the keywords and further readings. The mathematics behind it is actually really easy, and it's quite interesting. It's extremely interesting to see how people actually solve these knots mathematically. So, for example, if you have, so maybe you could figure out that this one was just a circle all along, but just simply unsolve it, like untangling them, yeah? So, yeah, this is one of the things which I actually have met, because I wanted to understand what the braiding is about, because Krista was talking about, we are using our saving data in braids, you know, and she was so happy, and I was so sad, you know, like, what are you happy about? I don't get it. So, what happens here is they use something which is called the non-abelian statistics, okay? Now, what the heck is that, isn't it? Now, I failed to mention that Peter Tate with Kelvin, they were thinking about something which is called the superfluids, okay? Which are mediums where things do not actually have a resistance. This is one of the things why supercomputers are actually, not supercomputers, the quantum computers are actually being cooled down to almost 0 kelvins, like it's a hair above 0 Kelvin, right? And this is for a very good reason, because once you actually induce a, once you actually like freeze the atoms at a certain level, the resistance of the conductors actually start to drop. They actually go to non-existence. And this is why people call it the superconductors, where electrons are just simply zipping through without any resistance whatsoever, right? And this is the only moment where you actually do not disturb the actual, you actually do not have a problem with the environment coming from outside. Because the problem with quantum computing is that if you actually even put this into a entangled state, if you put 2 electrons in an entangled state, you will have it for a fraction of a second and they are just gone, because the environment coming from outside and just simply hits it and just they are gone. This is it. You cannot do anything smart with it. So people start to put this in the vacuum chambers, and then they cool it down really hard so that at the end, like the environment is actually not disturbed. Now, in the Microsoft's keynote, one of the older guys at the beginning, like at the most left to you when you look at the YouTube video, the guy was talking about the fractional statistics. Now, here's the important part which I was talking about. You cannot break an electron into pieces. It happens when you cool things down, really, really down to that level, you can actually break that electron into, let's say, 3 pieces. And every piece can have 1/3 of an electron. Okay? Now, this is actually quite interesting, because the problem is it doesn't really break in the terms when you imagine it. But they are actually really breaking like into, let's say, 3 pieces, and each one of those are actually connected. Now, the interesting part here is these pieces, they are called anyons. Okay? This is it. And the question was, what happens when I actually do this? You see this awful animation? 2 hours, just right there. Just wasted on this crap. So, yeah, I hate PowerPoint. It just says, hey, I'm a professor and I'm boring. So yeah, but you cannot do anything regarding it, right? So what happens when you exchange 2 anyons? When you just simply rotate them around each other. What happens here is, if you look at bosons, if you put them, you actually exchange their positions, nothing happens. Okay? And the same thing for, yeah, I think the bosons are like this. However, fermions, when you grab them and you just start rotating around each other, now you have 2 possibilities, 2 possible outcomes. You have something which is called the abelian outcome, which is the abelian statistics, which when you calculate the math of it, they start to analyze, the quantum state doesn't change. However, there is another outcome, which is this non-abelian outcome, which says that once you exchange those 2 guys' positions, the quantum state of your system changes. Now, how they are actually changing this, they are using something which is called the quantum Hall effect. And in order for them to perform this, they put T-junctions. And if you would like to exchange 2 particles, like two anyons position, what you will do is just simply take this guy, push it through down, take the other guy, push it there, and take this other guy and push it the other way. And right now you rotated them in place. By the way, this is all happening on a 2D surface. This is a 2D world. Okay? So, read about this or research about the quantum Hall effect if you are actually interested in exactly the names or exactly the effects of that thing. So, what happens here is, this is what they were talking about at the keynote. I stolen this from the Scientific American. Stealing is bad, but what can you do? So what happens here is, when you actually take an anyon and you exchange their position, you change the quantum state. However, when you actually make this evolution over time, they look like braiding. And if you in fact Google just non-abelian statistics, you will get a lot of diagrams that look like this. Okay? And yeah, so once you exchange them in one way, counterclockwise or clockwise, you start actually getting different results. And by the way, they are not intersecting. It's a very, very important thing to mention here. And this, what you see in the bottom, this is your C-naught gate. This is how it actually looks like. Theoretically, one of these interesting lectures, I forgot what was the guy's name, but once you search about this non-abelian statistics and topological quantum computing, he will say that theoretically you can actually form a gate with moving one particle. So once you braid one particle, you make just a one gate, which is actually quite interesting. Now, what Microsoft is actually trying to do is that they are actually trying to write a one more layer, which is the optimization layer. So they actually start to minimize a certain, the Krista was saying it's certain quantum gate. I couldn't find out what kind of quantum gate she's trying actually to reduce the usage of. So I implore you to research, hopefully to understand why there are certain quantum gates are dangerous that could probably collapse the whole thing. Now, the error rate is very important here. IBM's error rate is 10 to the minus 3, okay? Whatever, error factor of times 10 to the minus 3. This is the error rate of the accuracy rate. The outcome of your quantum program is probabilistic. So sometimes you need to apply it a couple of times in order to see the probability. If it rises, then this is it, okay? There are other quantum algorithms that has been outside since in the 90s. Deutsch's problem, I think the Shor's factorization. What are other grooves searching algorithm? How to search unstructured data? This is actually amazing thing to look at. Okay, so yeah, so this is it. This is how it actually physically looks like. These are the nanowires. This is how actually the braiding works. Okay, and they are actually contacted material scientists just to grow these crazy things, so can actually do the braiding correctly. All right, so I think there are just bringing up to the last things, which is the further keyword directions. Kalman invariant is very important if you would like to understand the braiding, how this braiding works, how to solve it. Learn about the math behind the quantum gates is very important. Non-abelian statistics are very important. Topological quantum computing is very important keywords to research for. And I guess these like 4 or 5 keywords which you have is going to be enough for you to put more beauty in the actual thing. Visit the IBM quantum experience. They have a very beautiful documentation, easy to read. It's easier than Microsoft's. And I think I would recommend that you read the IBM documentation, look at it, and so you look at the IBM documentation, then you read Microsoft's documentation. I think this could be the logical order. That sphere which you saw, which I presented to you for the qubit, is called the block sphere. Research that as well, so you can understand it more. Okay, so without so this is for the Dark Souls fans on Orlando, I think. This is my Twitter handle for those who are actually interested to contact me regarding graphics, please, not not quantum computing. And if there are any questions, I don't know. Honestly, I don't see anything online, so probably I will receive your questions then through the Twitter account. Do you have any questions, guys? Can you please go close? Thank you. Thank you very much. Okay. All right. Thank you. This is it. This is it. Okay.